Lucas is a statistician at Intel, and so he'll be talking about challenges in statistics in the semiconductor industry. And he got his PhD from Iowa State and has been around for a while here in the ASA Oregon chapter. And so we're actually pretty glad that he's here to sort of lead us as we move forward.
We'll see about leading. But okay, so what I've noticed in coming to a lot of ASA meetings is that you'd see most of the time the speaker would be academic, would be showing honestly very interesting problems, but unfortunately there wouldn't be a lot of folks in industry. So one of the things I kind of wanted to do over the last year or two was kind of give a glimpse. Now admittedly I can't show much in the way of data. People at Intel will come find me if I do, so can't do that much. So truth be told, you complained you didn't have very many formulas. If you didn't like her talk, you're not going to like mine. I have one. That's it. And most of you probably know the formula already. So that being said, this is almost more a discussion type presentation as opposed to a more formal, hey, this is what I'm looking at as far as research goes. So without further ado, I'll talk about some of the challenges that I've seen in the so I started at Intel 6.5 years ago. So share some of the things I've seen, and truth be told, some of these are some of the things Terry here sold me on when trying to hire me. So okay, so I thought first off I'd give a couple slides as far as what exactly happens within what we call the fab. So just manufacturing a semiconductor. Fortunately, it's not an easy thing to do. We try to make it look easy, but it's not. So what happens? So first off, we basically get handed silicon wafers. And so we batch them into lots, various number of wafers per lot, and we queue them around the fab in a very rather lengthy manufacturing process. Depending on what product we're selling, there's usually going to be a few hundred die, which become the chips that end up powering your computers, on each of these wafers. There are literally thousands of steps that a wafer could pass through. Depends on the product and what's going on before we assemble it into something that the customer will actually see. And so, not surprisingly, there's several different things that happens to these wafers as they go running around the fab. So just kind of give an idea. So the biggest groups we have. So here's kind of your lot of wafers. And so there's various different things that happens to them. So some of them, I know this planer isn't really on here. So that one, planer, all they do is polish the wafer in a very simplistic manner. Diffusion and metals, mostly what they do is you'll throw a whole bunch of wafers into a chamber, you'll spread some gas around, or in some case you'll have to put them in some sort of liquid and electrocute things, and things will deposit onto the wafer. Let's see here. So implant, they will actually shoot it with an ion beam to implant some ions into the wafer. Lithography, basically, so we say spin, expose, develop, and so we put on this film, I think is the word, right, Terry? But we put on yeah, resist would be the word I'm looking for. So, yeah, so we spin, expose, develop, put this resist in a particular pattern on the wafer. So then etch, obviously I think you can guess what etch is. It's you start etching into the wafer to dig things out and so on and so forth. And so then, once we do this a few thousand times amongst everything, we'll actually electrically test these things, and then we'll send them to a group called sort, where they sort things out to, hey, what can we sell, what can't we sell, so on and so forth. Okay, so job one for us is really to turn sand into gold. Okay, it's not quite gold at the end, but if we sell enough of it, it ends up being a pretty nice pile of it. So the silicon wafers generally are just made out of sand for the most part. So that's why I say the goal is from sand to gold. But obviously the more die on the wafer after we're done running it through all these processes that we can sell, well, the better off Intel is going to be. Okay, so as you might guess, one of the statistician's biggest goals is how do we make more gold? So obviously every step of the process, please don't ask me, I can't tell you for one, I literally can't tell you for two, so don't waste your time asking. But there's some questions obviously that we are called upon to help answer. So the most obvious one would be, how do we maximize yield? Obviously in a perfect world, every single die on the wafer would yield. Truth happened terribly often since I've got there. But the more we can do, the better off we'll be. In particular, in trying to help with that, so how do we monitor what is happening in line? So if we can measure something at litho that tells us instantly, oh, our yield is going to not be very good for this, obviously we can take measures to make sure litho doesn't do that. And then lastly, even how do we test our chips? The last thing we want to do is send a bunch of chips that we claim work, and then 2 hours after you turn your computer on, it goes pop, smoke starts billowing from it, and suddenly you're going to be coming to us with a request to return your chip. Well, actually, you're probably going to Dell or HP or someone to return the computer, but they're in turn going to come ask us and say, hey, what's going on here? Your chips are causing us trouble. So those are kind of the 3 main questions I'm going to go after. But so that's kind of how my talk is going to be. I'm going to look at the first one, the second one, and the third one. Okay, so maximizing yield. So you might ask, okay, what could possibly go wrong? Well, what can't possibly go wrong might be the shorter list. So just to give you kind of an idea of how complicated this is, the picture on the left is something that will make you sick. It's actually a picture of the influenza virus. Over here is a transistor from a few technologies ago. So in fact, we would, so let's see here. So I know we're working on 10 nanometer technology, so imagine now 5 of those in there. So it's always, one of the sayings I remember as a kid very well is, we made it by the hair on our chinny chin chin. And until that means we made it by a country mile. Because these are far, far skinnier than the hairs on your chin. So admittedly, in some cases, you can look at the data, and my 6-year-old could very quickly tell you, well, I can tell you something's not right here. Something's changed. But as you might guess, there are plenty of cases where it's nowhere near intuitively obvious. Okay, so just kind of giving a few mysteries a statistician might solve. So the most obvious, well, not really the most obvious one per se, but multiple factors may need to be met in order to create a defect. So, for example, a chemical reaction happens when the concentration of something is at, I don't know, 3 grams per liter. And it also has to be 237 degrees centigrade or higher for the reaction to occur. If you hit both of those, a whole lot of the wafer on the die are going to get something on it, and it's going to cause a bunch of shorts, and basically most of the chips on the die aren't going to work. Or most of the chips on the wafer aren't going to work. How can we determine that, yeah, it's at 237 degrees, and yeah, that gas concentration is at 3? So an engineer, by default, probably isn't going to have the knowledge to just up and figure out, okay, these are my conditions. So that's one example. So another one that we see quite a bit is we have measurements that are highly correlated with one another. Independence is a great thing, but as Maria's talk said as well, we don't have that very often. So if they're highly correlated, and it could be this structure or that structure, now we've got to play a game of whodunit. So not that even we can always solve it, but we have some tools that might be able to help point the finger more strongly at one structure as opposed to the other.
I think our imputation stuff we got to steal madly.
What you doing after this stuff? Indeed. So another one that we look at quite a bit is, what should the spatial profile of the wafer on the tool, spatial profile of the wafer be when a tool is actually done doing something to the wafer? So obviously, litho does something, and then etch does something, and then, interesting, you had CVD. CVD stands for something like chemical vapor deposition in our place. So they get done doing something. It may flatten things out. It may cause things to happen near the edge of the wafer. Could have things happen near the center of the wafer. So in some cases, you'd love it to just be perfectly flat everywhere, but because of the various chemical reactions and things that we do, that may not be desirable. You may end up killing a whole lot of dye on your wafer because of what's going to happen after what one module is done, based on what other people are going to do to it. So how do you determine what should that spatial profile be? And lastly, just as another example, so let's say you have a structure and people are going to deposit a whole bunch of some material on it. So let's say it's 50 nanometers thick. Come to etch, you have to etch through that 50 nanometers. So sure, we can say, okay, we're going to etch 2 nanometers a second for 25 seconds. But what happens if you get something that has 52 nanometers on it? Something like 25 seconds is still going to leave something in between and cause electrical problems later on. So if we use something along the lines of automated process control to help tell the tool, okay, I know from upstream there's 52 nanometers I need to etch through, so do it a second longer and get through there. Now it's a little bit more simplistic. Oftentimes there can be 3 or 4 or 5 or 10 other things that might impact it a bit, but just kind of a simple example of where it could come in handy. Okay, so I felt like we needed to have something funny in here, if nothing else. So obviously we talk about correlation a little bit, and so engineers honestly haven't had a great deal of statistics before they come in most cases. So we teach some courses, and so I like to, in one of our classes, talk about the usual warnings about correlation. So many of you probably know Randall Munroe's XKCD comic. So he used to think correlation implied causation. Now he took a stats class and knows better. Maybe the class helped. So he also has a tooltip or some such. When you put your mouse over it, says correlation does not imply causation, but it does waggle its eyebrows suggestively and gesture furtively while mouthing, "Look over there." So, and then one year, my mom got me a Dilbert calendar for Christmas, and this one showed up in November, and I laughed pretty loud when I saw that. So, for some reason, the pointy-haired boss always gets an email about the world's worst bosses when he goes to Dilbert's cube. Pointy-haired boss thinks he's figured out the correlation. Alas, Wally behind his cube, spoiling his plans. So
don't send that to our boss.
I haven't. Then again, he did look at this presentation. So okay, so thinking about correlation, how might a statistician solve them? So thankfully, we have many tools in our tool belt. So I can tell you about some of the things I can assure you we do. So it should surprise absolutely no one that we do design of experiments at Intel. And they vary from rather simple ones to a one-sample t-test, something that any undergraduate would see. We can go up to full factorials. We can do response surface designs. So varying complexity. Terry likes her definitive screening designs. So other things, so linear regression, not surprisingly, comes into play quite a bit. But then we also have to look at more complicated things when you have all sorts of interactions and lots of things going on. Sometimes simple models aren't going to capture certain things. So on occasion, I've been called upon to use classification trees. I've even used regression tree once or twice, but I don't generally use that as the final answer. Just been what's worked for me. And in some cases, the engineer may not care a whole lot about how things happen. He just wants to know what's going to happen. So in the case of that, something black box like a neural network could work. But even with these, we can't just come out and use these tools and expect them to work. I wish I could remember Yogi Berra's quote about things working in theory and in practice, but I can't remember all of it. So, okay, so unfortunately I'm going to start poking some holes in some of the things that we might do. So taking a look at linear regression. So with typical linear regression, we assume the predictor is measured without error. How many things do you think are measured in Intel without error?
Let's generalize that to the world.
Well, by error, if we're talking about 1/1000th of 1 nanometer, we're literally splitting atoms at that point. So it's not to say the error is this big when what we're measuring is only this big, but truth be told, it's probably not measured without error. So, one thing to think about is, should we be using simple linear regression? Of course, one way to look at it is, okay, my predictor, I'm only going to be off by 1,000th of a nanometer, whereas my response is going to be off by up to a nanometer. In that case, the ratio of variances probably says it's probably not going to matter much. But if it's a little more 50-50 than that, I don't know exactly where the boundary would be to do something in that situation, but then you may need to call upon something like orthogonal regression, which relaxes that assumption. Okay, so of course with any business, two things that are going to get in your way are time and money. So, of course, engineers are constantly trying to find ways to improve the process. So, of course, they do that. You can improve yield. You can reduce defects. You can increase throughput, which at least increases the number of die we end up getting out. And you can also decrease cost. So, in some cases, simply obtaining wafers to even experiment on can be difficult. So, I mean, yes, a single wafer has hundreds of sellable die on it, but obviously if it has a few hundred that you can sell, and we can sell each of those for a few hundred, you can guess how much money even one wafer ends up costing. So, even getting that at times can be difficult. So, I wish we could always say, oh yeah, we always have n equal 4,000. Yeah, no, it doesn't happen that way. So in some cases we have to play with small sample size issues. And of course, one of those issues might be, okay, I have 5 wafers. I have 45 predictors. As you might guess, yes, linear regression is not going to save you in that situation. So what can you do? So you can try something like a balanced incomplete block design if you know you're doomed before you even try to collect data. You can try using some techniques that aren't necessarily as picky about n being greater than p. So stepwise regression is one thought. Maybe it works, maybe it doesn't. An engineer may claim 40 things may affect it, but you may find out quickly, oh, it's only 3. I have hope at 3. So, or even something along the lines of the classification regression trees, as I mentioned earlier. Okay, so now I'm going to kind of transition over to what can we monitor in line to kind of help us with set yield. So as you might suspect with all those processes and whatnot, there's a whole lot of things we can measure. Of course, at the same time, we don't want to process a whole bunch of material when we already know it's not going to work. We've already screwed things up. So the questions we might want to consider here is, obviously, what should we measure in line? Where should we measure it in line? How often should we measure it? And even after we've even figured out what to measure, what constitutes that something is at least out of control? Now, out of control may mean a huge problem. Maybe it necessarily doesn't. So, a lot of things need to be thought about. So, as you might suspect, there's all those processes that we do to it. There's just no way to measure everything. There's just too much. In some cases, measuring things actually ends up being destructive. So, we don't have any dies to sell because we destroyed all of them measuring it. You can guess how much money we're going to make at this. So even the time waiting for it to test or to measure may allow, if you have it in air, well, some things in the air can react with what's on the wafer and end up destroying what's on the wafer, and in the end ends up destroying things. So thus, we really do have to be careful to measure what's important and also do so in a timely manner in some instances. So, one quote, we are drowning in information, yet starved for knowledge. So it's really kind of where we're at on a lot of things. Okay, so what's important? So hopefully measuring something that causes, or at least hopefully correlates to yield, should be measured. There's more to consider. So for some structures, we advertise to customers that they're going to be this wide or this tall or some such. So obviously if we're telling the customer it's going to be this, most of the time we probably should be measuring that to make sure we're actually doing what we say we're doing. So other things to think about. So there are some measurements, so we try to check whether there are particles on the wafer. Obviously particles can react, can do various things, and kill die on our wafers. We would prefer that number to be 0 all the time. If it's 0 virtually all the time, that's not a terribly normal distribution. So then, nice normal theory, which is really nice, warm and fuzzy, we don't have that option anymore. So that's something to think about. We need to measure things that are indicative of the tool's health. And so, by health, we generally have them, hey, you're going to send out this much gas for this long. We want the temperature inside the chamber to be X temperature. We need the pressure to be Y, so on and so forth. Over time, those might change depending on what's in the chamber. I mean, chemical reactions happen not only on the wafer, but unfortunately outside the wafer and inside the chamber, and that can cause various things to happen as well. So oftentimes some of those can actually give us a warning that, hey, we need to go in there and clean that chamber, or we're going to start killing die and killing wafers. So hopefully we're measuring that to enable to figure out when we should perform some preventative maintenance. Okay, so one of the things we tell the engineers is, know thy enemy, his name is variation. I've also told students, if you don't like me, reduce the variation in your module to 0. I assure you, you'll never see me again. That being said, no one's actually managed to successfully complete that challenge. So, and here's probably why. So, just kind of giving you an example of just all the places we can see variation. So, just for a moment, suppose we measure 5 sites on 3. You can think of it as 5 die on 3 wafers within a lot. Where might we find variation? Well, lot A, lot B, lot C might be a bit different, and so there's variation there. The wafers within a lot could be different depending on which one you process first, which one you process second, so on and so forth. Within wafer, so we talked about should the profile even be perfectly flat, should it be a little bit different? So some of these tools, the way they're set up, take more than one wafer at a time. So they have multiple chambers. Are those chambers the same? Now let's throw even more fun. Some of those chambers have subchambers. So 2 wafers go into a chamber, 1 goes into each subchamber. You think those subchambers are exactly the same? So needless to say, I've already given you 5 different places there could be variation that we have to segment out. Never mind what could have happened 3 places before them, 5 places before them, so on and so forth that may impact things. So needless to say, this may well not even be close to an exhaustive list. So analyzing these in some cases, certainly not trivial. So just to kind of give a picture of the 5 sites on 3 wafers per lot. It could look something like this. So you have your die on your wafer, we measure, pick 3 out of there, pick 3 out of there, pick 3 out of there. And you can very quickly look at your data, do all sorts of variance analyses, and see that, yep, there's some here, some there, some there, some there, some there. And as you can tell, it's certainly not a trivial exercise. And so there are projects where they're looking to reduce the variation at most of these levels. Okay, so we get done monitoring everything in line to get to the end, and so now we need to start testing. So we finished processing the wafer. We need to figure out, hey, what can we package and later on actually sell to our customers. So as you might guess, as far as testing, so many of these die, each die will have 1 billion transistors on it. Now, if there's 300 die on each wafer, you think we can really test 300 billion transistors. And that's just one wafer. Now throw in all the lots we do in a week. Good luck. Okay, so no surprise, we're not checking it. So what can we check? Well, if there's only a few hundred die, we can do some tests to figure out whether the chip works. We don't necessarily have to check every single transistor to figure out, oh, enough of them are dead that we can't sell this. We can check its performance. So if we tell folks, hey, this is a 3 gigahertz processor, is it really 3 gigahertz? It's one thing if it turns out to be 2,999.98. I don't think customers are going to get too upset there. But if it ends up being 2,820, I don't necessarily know where that line is, but at the least, if we tell people it's 3 gigahertz, it should be roughly 3 gigahertz. So not only that, but we also do some stress testing. As I mentioned in the example earlier, the last thing we want to do is have HP sell a computer and 5 hours later, they give it back to HP saying, the Intel chip blew up. So, okay, so thinking about the life of a chip, there's many things that could cause it to fail. So a low hazard function is the one function I will share here. I suspect most people here have probably seen it. So of course we can think of the hazard rate as the instantaneous fail rate at time t. And so really in the case, not surprisingly, we look at kind of a survival analysis of the chips as well. We do tests to make sure they last a few years and whatnot as well. So simply looking at the good old bathtub curve, you might not much surprised to find, hey, we generally have some that die really early. We get to this period where not very many die at all, and then as they get old, now the rest of them will die off. Okay, so a failure very early in life is called infant mortality. So one of the things we could do is essentially fit a defective subpopulation for life distribution. And basically estimate, hey, how many of our chips are going to suffer from this defect that'll kill it early in life? Obviously, we want that to be 0, but if it's not, we need to figure out a way to monitor, hey, how are we going to fix this? So, good news is, in some cases, if it's only going to be very early, we can actually do a burn-in, figure out which ones are going to die, and make sure Kathy and her friends never see those chips. So then she doesn't have that problem with folks coming back with, why did my Intel chip blow up? So we have that. So as far as investigating chips that make it to the wear-out phase, well, as you might suspect, generally they last years. I don't have a chip, multiple technologies into the future that we're already testing. We don't have it. So how can we go about doing that? So we actually use accelerated life testing to at least make an educated guess at it. So as far as accelerated life tests go, we have a rough idea of the typical conditions a chip will endure. We call these use conditions. So if we increase, generally the temperature and the voltage are going to be the big ones you can modulate fairly easily. So if we ramp those high up enough, we can get a lot of chips to fail fairly quickly. And so then we can collect data and do analyses on that. Don't have to wait 3, 4, 5, 10 years. So what kind of data do we have? Well, varies on the situation. I've seen some cases where we have a device that'll say, oh, it died after 35 minutes. And so in that case, we actually have exact data in some cases. Quite a few cases, we don't necessarily have exact data. Someone will check every so often, hey, did everything still working in that oven? Oh, those 3 are done, get them out of here. But then, hey, I checked at 20 hours into the study, now I checked 30 hours into the study. I don't know exactly when it failed, but I know it failed somewhere between 20 and 30, so I have my interval censored data. But also at the same time, we don't have time to test. We may not even have time to test until every chip kicks the bucket. But if we can get a fair number of them too, that's enough to get a fairly decent estimate of life distribution. And so in that case, we can still use right censored data to help us improve our estimate while saving time. Okay, so to analyze such data, so accelerated life testing, to me, generally is linear regression with 3 differences. So we're taught in linear regression, hey, you want the residuals to be normally distributed. You can use a normal distribution here, but generally for this, that's not going to work terribly well. So we generally use other distributions than the normal. So bad news is the likelihood function changes a bit, but the good news is we generally use distributions that aren't terribly hard on a computer to go figure out what the parameter estimate should be. So the second one's kind of my favorite. So I remember asking once, so take for example predicting height versus weight. So in the data set, everyone's between 60 and 65 inches tall. And I said, oh, I want to predict someone who's 6 foot tall. Teacher's like, you're being extrapolating. Don't do that. Well, here in accelerated life testing land, the whole point of doing this is to be able to extrapolate back. So if you didn't like that when you did simple linear regression, good news. You can do that here. So lastly, we also have the aforementioned censored data. So generally in simple linear regression, you're going to always have exact data. But we know now with the techniques we have today, we are not necessarily bound to those. Okay, so that's for the most part my talk. So just kind of conclude things. So the 3 big questions we try to ask ourselves is, how do we characterize yield? What do or should we measure in line? And how do we determine how reliable our chips are? So it's interesting to me. I say we have a great deal of data, and we do in many cases, and yet I've explained other instances where you get told, you will get one wafer to figure this out. So it's interesting at times that, yes, we have a little bit of a balance of scales, but obviously a lot of this comes down to time and money. Hey, how important is this? How much are you going to promise me? I mean, if I told the right person, hey, if you let me experiment on this, I guarantee you every die on every wafer will work. I'm pretty sure I'll get most of whatever I want. But if I don't deliver, I might well be walking out the door. So obviously there's always a balancing act to be done here. But that being said, as statisticians, so So if we overcome those challenges and help the fab create more die that work, well, and work as long as we say it's going to work, then we have happy customers, happy business, so on and so forth. And that's it.
Any questions?
Do you have trouble talking to the engineers and fabrication people about explaining how your statistical methods should work and how they are working, or did they more or less accept the conclusions you give?
It's kind of a... So we actually do teach some statistics to the end. We actually offer courses. I'm in the midst of teaching a design and experiments course right now. And probably not surprisingly, there are some engineers that happily accept us and happily accept what we're trying to teach. There are some that look at us kind of indifferently, and there are others that would love to take us out back. And so it's a little bit of everything.
But they only want to take us out back when the data proves their theory wrong.
Which is true everywhere.
Yes. Yes.
Any other questions? If not, then let's thank Lucas and Maria for such great